Hi folks! The following video is our fourth one on mechanistic experiments. I'll be talking about mechanistic tools beyond isotope effects and Hammett plots. The very first thing an organic chemist should do when trying to understand a reaction mechanism is make sure they have identified all of the products. This sounds straightforward, but it is overlooked surprisingly often. If you can, it's important to identify all of the products of the reaction, including the minor ones. The identity of minor products can provide clues as to what the mechanism of the reaction is, or if the reaction forms a product that you didn't expect, you could potentially misinterpret kinetics data if you didn't go through and verify what product was actually formed. For example, let's consider the following reaction. I have a benzylic alkyl chloride that's being treated with sodium hydroxide. Researchers did the kinetics experiments for this reaction and determined that the rate was first order in the alkyl chloride and first order in sodium hydroxide. The expected product of this reaction is the substitution product. We would expect an SN2 mechanism to have the rate law of the form shown below. However, the actual product was this substituted alkene instead. The sodium hydroxide actually functioned as a base to deprotonate the carbon with the chloride attached to it, which then undergoes a more complicated reaction, eventually leading to this stable alkene. If the researchers had not identified this product correctly, they would have made assumptions about the mechanism based on the rate law that would be incorrect. Another common mechanistic tool for organic chemistry is performing stereochemical analysis. Starting out with one stereochemistry of starting material, figuring out what the stereochemistry of the product is, and using the stereochemical outcome to give you information about the reaction's mechanism. As an example, let's consider two possible pathways for substitution reactions of alkyl halides. Let's consider the following alkyl bromide, where in this case the alpha carbon, the one attached to the bromine, is a chiral center, and it is also allylic, being adjacent to an alkene. In an SN2 potential mechanism, the cyanide nucleophile would attack the alpha carbon, and the loss of leaving group would occur in the same step. The SN2 reaction causes an inversion of stereochemistry at the alpha carbon. So if an SN2 reaction had occurred, the cyanide group should be added as a dash in this molecule's orientation. Now let's consider an SN1 potential mechanism instead, and what its stereochemical outcomes should be. In an SN1 mechanism, the first step would be a loss of bromide leaving group event. This would form a secondary and resonance-stabilized carbocation. The carbocation is electrophilic, and it could be attacked by the cyanide nucleophile in a second reaction step. The carbocation is planar, and the cyanide nucleophile could attack it from either above or below. Because of this, the SN1 mechanism gives rise to two stereoisomers of product. One where the cyanide was added from below, making it a dashed bond, and one where it was added from above, giving this group a wedged bond. So for this one alkyl bromide starting material, by tracking the reaction's stereochemistry in its reaction with a cyanide nucleophile, you could determine whether or not the reaction proceeded by an SN2 pathway or an SN1 pathway by seeing if you either form one stereoisomer of product or a mixture of two enantiomers. The stereochemical analysis would allow you to identify your reaction mechanism that was operative. Another common mechanistic tool is trapping of a reactive intermediate. The idea here is if you have an intermediate that is either too unstable to be observed, or if it appears after the rate determining step so you can't observe it, you can potentially still trap it by reacting it with an added reagent. If you had a carbocation that is potentially forming in your reaction, a good trap for that would be a nucleophile. The nucleophile could attack the carbocation to give a substitution product. A good reagent for trapping a carbanion, if it forms, is carbon dioxide. Carbanions are good nucleophiles, and the carbon of the CO2 molecule is electrophilic. If a carbanion is formed in a reaction where there is carbon dioxide present, those will react with each other to generate a carboxylate anion. So if you were unsure if you were making a carbanion, you could try your reaction with carbon dioxide present to determine if this reaction takes place. If it did, that suggests that there was a carbanion present. Another common trapping agent for either alkenes or alkynes is to add dienes in order to trap them in a Diels-Alder reaction. As an example, let's consider a researcher wanted to know if a cyclic alkyne was forming in their reaction. Let's consider the following alkene that's being treated with a base. The base could potentially deprotonate the hydrogen that is beta to the bromine leaving group. The electrons from the CH bond could go to form an alkyne, and loss of leaving group could occur in an E2 step. This elimination, if it occurred, would form a cyclic six-membered ring alkyne. We would expect that this would have a short lifetime because it is strained. The ideal bond angles for the alkyne are 180 degrees, and it cannot achieve those bond angles in such a small ring. What you could do is try to run this reaction in the presence of a diene. You'd imagine in your first potential reaction step, you could have the elimination reaction to generate your very reactive, strained alkyne intermediate. And alkynes are reactive in Diels-Alder reactions. So imagine performing the reaction in the presence of a diene. If the cyclic alkyne formed, it could undergo a Diels-Alder reaction, where I've drawn out the mechanism here. And this Diels-Alder reaction would form this following product, which features two six-membered rings. So, if you performed your deprotonation reaction in the presence of a diene, and you observed this product, it would suggest that this intermediate had formed, even though you weren't able to see that intermediate itself. Another type of mechanistic experiment similar to the trapping one is known as a competition experiment. This is useful when you want to get information about reaction steps that occur after the rate determining step. As a reminder, these will not be reflected in the kinetics for the reaction. In the competition experiment, you would add two or more reagents that could compete in reacting with the same intermediate. So let's consider you had a reactant, and your rate determining step was formation of an unstable intermediate. Imagine some trapping agent A reacts to give a product 1, and a separate trap B reacts with the same intermediate to form product 2. This intermediate could be a carbocation, a carbanion, or a radical, or a carbene, just something reactive. In the case where the intermediate was a carbocation, your trapping agents could be something like two different nucleophiles. And what you would be looking at is, in the product, which nucleophile reacted with the intermediate faster. So even though the reaction of the intermediate with the trapping agents occurred after the rate-determining step, the product ratio tells you about the ratio of the rate constants for your trapping steps. So let's imagine you had a 60% to 40% product ratio for products 1 and 2. And let's call the rate constant for the reaction of the intermediate with trap A, Ka, and the rate constant for the intermediate reacting with trap B, I will call Kb. The product ratio of 60 to 40 tells you that the rate constant ratio is 60 to 40 as well, and you could simplify this to a 3 to 2 ratio in this case. This tells you that the rate constant giving rise to product 1 is greater than the rate constant giving rise to product 2. A useful application of competition experiments is checking two reactions to see if they form the same type of intermediate. Often similar reactions you would expect to generate similar intermediates. And what you could do is perform two competition experiments. If you get the same products and they form in the same ratio for your two different reactions, it will suggest that the same intermediate was formed in the two different reactions. Let's imagine a tertiary alkyl iodide losing its iodide leaving group to form a carbocation. In your competition experiment, you would have a mixture of two nucleophiles around. I'm just going to call them nucleophile A and nucleophile B, but these could be any two different nucleophiles. The carbocation intermediate could react with nucleophile A to give one substitution product, or the carbocation intermediate could react with nucleophile B to give a different substitution product. Now imagine, what if we had just started with a tertiary alkyl bromide instead? We would expect this could also lose its leaving group to generate the same tertiary carbocation intermediate as in the alkyl iodide case. In your reaction with the alkyl bromide, you would also want to treat it with a mixture of two nucleophiles, and you would want to look at the product ratio here as well. If you get the same ratio of your two products, starting with either the alkyl iodide or the alkyl bromide, that suggests that both reactants formed the same intermediate, and then it underwent two separate reactions from there. If you did not observe the same products in the same ratio, it would suggest that you had not formed the same intermediate from your two similar reactions. A separate type of experiment, known as a crossover experiment, tests whether a reactant breaks apart into separate intermediates that then recombine to giving a product. The other possibility being that the reactants stayed together and underwent a solely intramolecular reaction. What you would do is perform one experiment with a mixture of two very similar reactants in the same flask. One of those reactants needs to be labeled so you can tell it apart from the other reactant. This type of label could be different isotopes or different substituents. As an example scenario, let's consider we had a molecule with a bond between A and B, and our product is CD. And let's consider a reaction of A star B star. Let's assume this forms C star D star. So, in your crossover experiment, you would have both AB and A star B star present in the same flask. There are two possibilities for the types of products that could form. One possibility is that you only get CD and C star D star. We would call this a case where there is no scrambling. This result suggests that the reactants did not break apart to form free intermediates. If instead you saw 4 products, CD, C star D star, but also CD star and C star D, we would say that scrambling has occurred, and this result would suggest that your reactants, AB and A star B star, broke apart at some point during the reaction to form free intermediates, and then these recombined to give more products. As an example of a crossover experiment, let's consider a reaction known as a Claisen rearrangement. We'll consider 2 potential mechanisms that we want to distinguish between. Here is the starting material for a Claisen rearrangement. In one potential mechanism, I have a concerted reaction with 3 curved arrows. This forms the ketone and alkene of the Claisen product in a single step. An alternative mechanism to consider is, what if the carbon-oxygen bond broke first in this reaction? This would form an enolate anion and an allylic carbocation. In a separate step, you could have the carbon-oxygen pi bond formation, carbon-carbon single bond formation, and pi bond moving. This would generate the same final product. So, as an example of a crossover experiment, let's consider a single reaction where we had these 2 similar reagents present. One of them has no methyl groups present, and one reagent has 2 methyl groups present. One possibility is that the only 2 products you observe have either no methyl groups present or 2 methyl groups present. If only these 2 products are observed in the crossover experiment, this would give support to the concerted mechanism shown above. Another possibility is that you have 4 products formed. One with no methyls present, one with 2 methyls present, and 2 products with 1 methyl present each, either close to oxygen or further from oxygen. If you saw these 4 products in your crossover experiment, it would support the 2-step mechanism shown below, rather than the concerted mechanism. Another type of mechanistic experiment looks at isotope scrambling. You're just using isotopes as a useful tool for keeping track of where atoms are in your reactants compared to products. What you would do is isotopically label some part of the reactant and just figure out where those labels end up in the products. The most common isotopic labels are either deuteriums or carbon-13s. Here again, I want to consider the Claisen rearrangement. And an example of an isotopic scrambling experiment is putting 2 deuteriums on the lower carbon attached to oxygen in your starting material. One possibility is that only the product in which the 2 deuteriums are on the end carbon is formed. If only this product is observed, that would support the concerted mechanism for the Claisen rearrangement that I drew on the previous page. Another possibility is that 2 products could form that differ in their placement of the deuteriums. If in your reaction you observed a mixture of these 2 products, it would suggest that your molecule broke into 2 intermediates at some stage. If the top half of the molecule completely detached from the bottom half, your molecules could come back together either with the deuteriums on the left or with the deuteriums on the right to give the other product. And last, I want to discuss one type of mechanistic experiment that specifically probes whether or not radicals are formed in a reaction. This is known as a radical clock. The idea here is to trap a suspected radical intermediate. The radical clock is going to take advantage of intramolecular radical rearrangement reactions. The radical clock will have specific placements of the radical relative to other functional groups that can undergo rearrangement. And these radical clocks, these particular motifs, have well-known rate constants for these rearrangements. One example is having a radical at this position relative to an alkene. This radical would undergo a rearrangement to form a 5-membered ring with an adjacent radical. This reaction occurs with a rate constant of 1 × 10⁵ inverse seconds. So let's say you had a reaction that formed a radical at this position, and you had conveniently placed your alkene here. If you saw that the radical rearranged in this way, it would not only tell you that a radical had formed, but it would also tell you approximately how fast the rearrangement must have occurred. Another example is that a radical that is adjacent to a 3-membered ring can open up the ring to form a radical that is 1 position away from an alkene. This radical rearrangement goes even faster with a rate constant of 1 × 10⁸ inverse seconds. And a final example of a radical rearrangement reaction that can be used for oxygen radicals is having an oxygen radical off of a 5-membered ring. In this rearrangement, a very strong carbon-oxygen pi bond forms, and a carbon radical forms as well. This occurs at a slightly lower rate constant of 8 × 10⁷ inverse seconds. We'll work through some examples in class, but the general idea here is that if you embed these motifs into your molecule, you can determine if a radical forms at these positions because it will undergo these rearrangements at these rates. All right. So this video talked about a variety of mechanistic tools. I mentioned the importance of identifying the products of your reaction, and also talked about using stereochemical outcomes to assess a mechanism. I talked about trapping reactive intermediates, which can also be done in competition experiments. I also talked about what are known as crossover experiments, which can determine if your starting material breaks into 2 or more pieces during your reaction mechanism. And I've just briefly mentioned the idea of radical clocks to assess whether radicals form in a reaction mechanism. That's it for this video. I will see you in class.